Hi class, we are here for the next video. So we are going to cover chapter 8.3, non-homogeneous linear systems. So basically same thing that we normally do. We'll talk about the homogeneous system, and then we'll look at a particular solution for the forcing function, right? Or the non-homogeneous part of our equation. So a lot of things are going to be familiar from the last two sections, obviously, and very similar to what it is that we do from doing a single DE, right? So we can apply, generally what we do is we apply the variations parameters method. So let's go ahead and get started, okay? So another method that we use is undetermined coefficient. So this is how we started off talking about DEs in for single higher orders for the non-homogeneous case. So we'll sort of do the same thing, right? So again, we're making assumptions about our particular solution based upon what our forcing functions look like, right? So our functions look like this: x prime equals ax plus our forcing function based on t, right? So based on the form of the forcing function, we'll kind of determine what our particular solution looks like, right? So we do this the same way as we normally do. Solve for our homogeneous equation, the general solution. We form the generalized particular solution based on what our f of t looks like. And then we solve for x of p based on x of p being a solution to my differential equation, right? And then using this assumption, we can then solve for any unknowns that we have, constants, things like that, right? So this method works very well, just like for higher order differential equations in a single equation, when my forcing function is comprised of constants, polynomials, exponential functions, sines and cosines, those kinds of forms, right? And finite sums and products, combinations basically of those types of functions. Okay, so this is not going to work well for things like rational functions and other logarithmic functions, right? Things like that. So this should be very, very similar to you, right? This is the exact same generalizations that we had for the particular solutions from chapter 4.4, 4.5, whatever our undetermined coefficients chapter was. Exact same picture, right? So the way that we form these general solutions is the same way that we did back then, right? It's just now we'll have n of those forcing functions, so we'll have n general forms inside of our particular solution vector. Okay, so let's go ahead and do an example. Okay, so let's say we want to solve this system with the functions sine of t and -2 cosine of t as our non-homogeneous functions, right? Our forcing functions. So my characteristic polynomial is going to be the determinant of lambda I minus a, right? So that's what lambda I minus a looks like. We're finding the determinant. So it's always easy when we have a 2 by 2 because we just multiply those and then subtract the product of the non-main diagonal, right? The cross diagonal. So I know that this is lambda squared minus 1 plus 5. So I'm going to have lambda squared plus 4, basically. Okay. So my solution here will give me a complex solution plus or minus 2i as my roots. So remember, complex solutions are actually kind of nice because I don't have to find two eigenvectors. I just find the one, and that will automatically give me my second, but I only need the one to form my solutions. So plugging in 2i for lambda, I will have 2i plus 1, -5, 1, 2i minus 1. Okay, I set that equal to 0. Do this by hand. If you have a nice calculator, you can do this on your calculator. That's fine. But you should come down to a reduced form of x1 equals -1 plus, or sorry, x1 plus -1 plus 2i x2 equals 0. Obviously, I need to move this to the other side. And so this is our relationship, right? I let x2 equal 1, then x1 equals 1 minus 2i. So that is my eigenvector. And remember, we want to separate this into the real and the imaginary portions, right? And then that lets us get our general form of a solution, right? So I have my real parts and my imaginary part, which gives me my general solution of in this form, right? So I got my C1. Remember, there's no alpha, so there's no e to the 0t is just 1. The beta is 2, so beta is in here. And then on the second part, you still have your real and imaginary, but then the sines and cosines switch the order, right? So for my general form of a solution, remember that I need to have, whenever sine or cosine pops up, they both show up in the general form of your solution for undetermined coefficients, right? So here, just sine of 4x, my form, my generalized form is a cosine 4x, b sine 4x. Same thing if it's just a cosine. So since there's a sine and a cosine here, for the first function, we're going to use some constant times cosine plus some constant times sine. And then for the second x2 function, it's the same thing, b1 cosine plus b2 sine, right? So now my goal is I'm going to take this. It needs to satisfy this equation, right? So I'm going to plug everything in and try to solve for this x prime p, or I'm sorry, for this xp function that I need. So I'm basically going to try to solve for a1, b1, a2, and b2, right? So doing this gives me the following. So this is x prime of p. Okay, remember, cosine turns into negative cosine, sine turns into cosine, right? So sine and cosine, everything here changes signs. I have my a, so this is x prime, a times that x plus the forcing function. So now I just combine everything together and I solve. So what does that mean? It means multiply this out, add this, subtract that. It's going to be equal to 0. So I'll have some functions equal to 0, and then I can start to solve for my a1, a2, b1, and b2. Okay, so we'll do that slowly. So the first thing I do here is I pull out the cosine and sine, and this a1, b1, a2, b2, and I turn it into its own multiplication problem, right? So if I multiply these two, this matrix and this vector, it looks like this form, right? So again, the more familiar you are with multiplying matrices and vectors, the easier the section is going to be for you, right? So instead of just trying to distribute this across, I could just turn this into a matrix so that I can now start just doing a bunch of matrix multiplications, right? So same thing here, I turn this x prime of p into a set of matrix multiplications as well. It just helps me to kind of solidify stuff. So I'm going to just start moving stuff around, right? So the first thing I'll do is I'll subtract this. So I subtract it over, okay? So I have my a times xp minus my xp prime plus my f function is how I decided to put this together. So I know that 0 is, and basically what I'm going to do is I'm going to start to multiply all of this stuff out, right? So I'm going slow here, but the first thing I'm doing is I'm multiplying these two together, right? This matrix and this matrix. So I got negative 1 a1 plus 5 b1 times cosine, right? Negative 1 a2 times 5 p2 times sine of t. So again, this is just me being very, very familiar with the way that matrix and vector multiplication works, so I can do them all at once, right? Here I'm going to get the same thing, negative a1 times a negative sine t, negative a2 times a cosine, okay, plus this forcing function sine t. So that's all my first row, and I'll do the same thing for the next one. Negative a1 and b1 times cosine, okay, negative a2 plus b2 times sine, okay, negative a1 negative a1 minus b1 negative sine, okay, and then same thing here. So I have my negative 2 cosine, my negative 2 b cosine, and my plus b1 sine. Apologies, I'm multiplying this times that, right? So b1 times the negative sine, so negative b1, negative sine, positive sine, negative b2 times the cosine, negative b2 cosine, minus t cosine here, right? So that was how we multiplied the matrix times the vector. So now I basically know that this equals 0 and this bottom part equals 0. So before I even want to start getting into that, I would like to combine these things as much as possible, right? So there's a lot of sines, a lot of cosines. So I'm just looking to try to like simplify the best of my ability, right? So ideally, to be honest, I would like to get all of my sines together, and I'm just going to pull out the common term. I get all of my cosines together so that I know what needs to be here, right? Multiply times cosine and what needs to be multiplied times sine, right? So that's kind of where I'm going to start looking for it. Okay, so this is what I have. So what I'm doing is cosine and sine. So these are going to be everything that has cosine. This is going to be everything that has sine. Okay, so first equation cosine, first equation sine, second equation cosine, second equation sine. So again, the better you are at multiplying matrices and vectors, the easier it is to get through these sections, right? So here you see I have my negative a1, 5b1. Okay, the other cosine is a negative a2. Here my sine in the first equation is negative a2 and a 5b2. Okay, an a1 and a single sine. Same thing here, negative a1 plus b1 is cosine. The next cosine is this negative b2 and a minus 2. And then this is my sine stuff from the second equation as well. Negative a2, b2, and a positive b1. Okay. The only way for this to equal 0 by multiplying times cosines and sines is if each of these parts are equal to 0. If this is 0 times cosine plus 0 times sine plus and then 0 times cosine and 0 times sine, that's really the only way to get zeros here, right? Because these things can vary in so many different ways. There's really no other ways for me to get this to work, right? So I'm going to set each of these equations here equal to 0, and that becomes my new system of equations that I need to solve. Okay, so I'm going to take this and I need to solve for a1, a2, b1, and b2, right? So this is my system of equations. All of my a1 stuff is here, right? All of my a2 stuff is here. All of my b1 stuff is here. All of my b2 stuff is here. So I took this and I just reorganized it as negative a1 minus a2, okay, plus b1, 0 b2s. Okay, so I want a1, a2, b1, b2 in the second equation. a1, a2, b1, b2 in the other one. So all of these align with a1, all of these align with b2, all of these align with b1, all of these align with b2. First equation, second equation, third equation, fourth equation. So I just reordered it so everything lines up the way that we like. And then the way that matrix multiplication works, this allows me to have a1 here. Every time I do that multiplication, it's always the first entry times a1. So these are all a1s, a2s, b1s, b2s. Okay. So in order to set it equal to this, remember there's several ways. I can do a reduced row echelon form. If this matrix is invertible, you can find that out by finding the determinant. If the determinant is not 0, then you can find the inverse, and you can just multiply this by the inverse of this matrix. If this is not invertible, then you need to solve using the RREF form, and then you'll have some funky answers in there, but you can still find an answer. Okay, so here I'm gonna do reduced row echelon form. So I'm putting this, and I'm putting those little dot dashes, and I'm putting this in here, right? So that's would be my setup. So when I reduce this, I should get the answer that a1 is negative 3, a2 is negative 1/3, b1 is negative 2/3, and b2 is 1/3. Okay, so therefore my particular solution now has solved for coefficients, okay? And this is the particular solution for my system of equations. So now I found my homogeneous solution, right? My general solution, and I found my particular solution. So we know we can use the superposition principle to add those two solutions together to create our single solution. So my generalized homogeneous solution plus my particular solution is the solution for my problem, okay? So, as you just saw, our next method that we have is variation of parameters. So if you think about what we had for a single higher order differential equation that was non-homogeneous, we had undetermined coefficients, we had the annihilator method, and we had variation of parameters. That was pretty much the only methods we had for solving non-homogeneous systems. So we are not going to talk about the annihilator method here. We've actually solved systems using the annihilator method, but it's not a method that's generally used. So the most common ones are undetermined coefficients and variation of parameters. The most used one is this method, okay? Generally generally people use variation of parameters. However, you can run into some problems, so I will preface this right now. I did try to solve this previous question here using variation of parameters, and it got very messy. And then I abandoned the whole thing. I was going to throw that at the end of this video. I was going to say, hey, look, we can use variation of parameters on this previous example. I chose a different example, obviously. But sometimes one method is better than the other. Okay, so I did try to use variation parameters on this problem, and it was super messy. Okay, we're going to do variation of parameters on a different example, obviously, and it's very clean, right? Whereas if I had used undetermined coefficients, it probably would have took me longer. So there's not really a way for you to say, oh, I'm going to use this method here or use this method here. You kind of just have to pick one, right? And if it's not going too well, switch to the other. Okay. Whoa. All right. Our solution that we're looking for, that is a linear combination of, so again, these are eigenvectors times the e to the eigenvalue t, or it could be combinations of sines and cosines if we have complex eigenvalues, right? So these are just those vectors that we're using in order to form our solution. So these are solution vectors, okay? These are our solution vectors. So if our solution is created of a linear combination of solution vectors to our non-homogeneous differential equation, then we can write it in this form, okay? We have C1, x11, x21, xn1. So these entries, right, are basically functions, okay? They could be sines, cosines, e to the whatevers, right? Because remember, these are solution vectors. Our solution vectors, depending on what the roots are to our homogeneous equation, has different forms. They also contain pieces of the particular solution that are coming from this forcing function, right? So we can change this into something that we're familiar with. Again, these are multiply times constants. We can pull these vectors together as a matrix, and we can write these coefficients as a vector, which we would call our vector of coefficients or a coefficient vector, and it would look like this, right? So we pull these together. These come across as a vector, right? So if we were to multiply these out, we would get basically this same thing, right? A linear combination rewritten as a matrix. So we call this matrix, right? This matrix with my functions in here, we call it phi of t. This is the fundamental matrix of the system on the interval. And this interval is the interval of existence that's shared for all of these functions and the existence of our dE, right? So x prime equals 8x implies that phi of t prime equals a times phi of t. All right, so again, this is a fundamental matrix. fundamental matrix, meaning that it's full of fundamental solutions. Okay, so if we let u of t equal a vector of functions, then we assume that the particular solution is a product of this fundamental matrix and this matrix, or I'm sorry, this vector of solutions, right? So again, we're following the variation of parameters method that we had from our single higher order DEs, okay? Then we're going to get x prime of the particular solution equals a times the particular vector plus the forcing function. So what we're going to do here then is we're going to substitute xp into this equation. So we need to differentiate it, right? And then we are also going to plug it in to this right hand side. So both of these are functions of t. So when you differentiate it, we're going to end up using the product rule, right? So here the derivative with respect to t of xp is going to be equal to the derivative with respect to t of the right hand side. So that derivative here is a product of functions. That's the product rule. Phi prime times u plus phi times u prime, right? That's the particular solution vector being differentiated with respect to t. On the right hand side here, we have a times this phi of t u of t plus the forcing function f. Okay, so this gives us this equation in terms of phi and in terms of u, that vector of arbitrary functions here that we are using to figure out our particular solution, right? So what I can do here, okay, is if you notice that phi prime is a times phi, so everywhere I see this phi prime here on the left hand side, I can replace that, which only shows up once though, I can replace it with a times phi of t, right? So I'm really just making substitutions into here, okay? So this stays the same, this part stays the same, but this phi prime I know is a times phi of t. Okay, so I have phi of t u prime, because if you notice this part and this part is the same, a phi prime of t u of t, a phi prime of t u of t. I could subtract that off from both sides, and I'm left with phi of t u prime of t equals my forcing function. Okay, so I can isolate my forcing function by multiplying by the inverse of phi of t on both sides. Remember, phi here is a fundamental matrix. Okay, it will have an inverse because fundamental matrices are made up of linearly independent vectors. Okay, I know they're linearly independent because I can write my solution as a linear combination of those vector functions x1, x2 up to xn. So I know these are linearly independent. If they are linearly independent, I have an inverse. So that is why I am able to multiply by phi inverse on the left hand side of both sides of the equation so that I can find my u prime of t. Okay, so if I want to find out what u of t is, I need to take the integral of this right hand side with respect to t. Okay, again, I know that this particular function is phi of t u of t. U of t now is this integral. So my particular solution is phi of t, that fundamental matrix, times the integral of the inverse of phi of t times f of t. Now this should start to look a little bit familiar to you. Okay, think about what we did in chapter 7, right? And x equals x of g, the general solution, plus the particular solution. So then if I plug everything in, my solution should be phi of t times this coefficient vector plus my particular solution, right? Again, we were assuming, not assuming, but we know that x written like this can be split apart times this phi of t times my coefficient vector, right? That is the solution for our non-homogeneous portion, or really just for our solution period. Okay, so using that, right, this is our C. We already talked about that. This is my particular solution vector, and this is my general solution vector. Okay, now notice that this is somewhat similar to what we would have for when we were looking at Laplace transforms. Okay, just the form of this integral. Just going to throw that out there right now. So let's go ahead and start our example. Solve x prime equals a times x plus f. So here for our forcing functions, we have some exponentials, which is actually generally pretty nice. And then we have our coefficient matrix, right? So I need to find my general solution in order to find my my general form. So I'm going to find the determinants, find my eigenvalues, my eigenvectors. So I have basically lambda squared minus 9. Okay, so that gives me plus and minus 3 for my eigenvalues. Plug those in for my lambdas. Okay, so I'll start with the negative one first. This is my system. If you notice, they will always be linear multiples of each other or constant multiples of each other in some form. So I should get 1, 2 equals 0. x1 plus 2x2 is 0. So that gives me x1 equals negative 2x2. If x2 is 1, x1 is negative 2, right? So my vector is negative 2, 1. Okay, that's my first eigenvector. For my second, I do the same thing. I plug in positive 3 for lambda everywhere, set it equal to 0, and I'm really going to end up with the same thing, but I'll have 1 and negative 2 equals 0, and I can tell because it's already very similar. Oh, it'll be a 1 and 4, sorry, 1 and negative 4. So from here, I move this over, x1 equals 4x2, that gives me 4, 1 as my eigenvalue, okay, my eigenvector, I'm sorry. I can put these together for my generalized solution, unknown constants here, okay, and so I can use this then to form my phi, right? So remember, my phi is basically made up of those vectors. So I leave the c1 and c2 out, they're just constant multiples. So those functions that I have based on these eigenvectors are negative 2e to negative 3, and 4e to the 3t, e to negative 3t, e to the 3t. So this is my phi, my fundamental matrix made up of the solution vectors for the homogeneous portion. Okay, so coming back, okay, I can really just jump straight into this. Okay, I just need my particular solution, so I can jump straight into this formula. I have my phi of t already. I need to find its inverse. I'm going to take my inverse and multiply it times the forcing function that I'm already given. Integrate each of the entries in there, and then take that result and multiply it times that fundamental matrix I just found, and then add it to what I already have. So it's pretty straightforward in the math, although I mean it's still quite a bit of work. Okay, so I need to find phi inverse of t. Again, finding inverses of 2 by 2 matrices are extremely easy. Again, review your linear algebra if you need help with that. So we find the determinant, which is this product and this product. And so that gives me 1 over negative 2 minus 4. Okay, so when I multiply these across, basically these exponents end up canceling each other out. So I don't have any e's or anything crazy in the denominator. It's just 1 over negative 6. Okay, I also have to, if you notice I switch these around, okay, I have to switch things around. So these two switch and these two change sign, and I multiply it by 1 over the determinant in order to find my inverse function for 2 by 2. Okay, so I swap these two locations. I change the sign on these two after I found the determinant, right? So it's the determinant, 1 over the determinant times, and then doing what I need to do for the 2 by 2. And so this is my phi inverse function here. Okay. I need to multiply these two together because that's what I'm going to take the integral of. So I'll take my phi inverse. I will multiply it times my forcing function here. Okay. So that's what I get. And I obviously will actually multiply it out, right? So this will change my exponents just a little bit, right? So I'm taking this row vector times this column vector and basically doing a dot product, and this row vector and this column vector and basically doing a dot product. Okay, so that's the result that I get. That is my phi inverse of t times f of t. Now I have to integrate this with respect to t. Right, so in order to do this, I'm basically just integrating each of these functions separately, basically, right? So there's one function to integrate, there's another function to integrate. Again, notice that my exponents are not all 3's anymore because of the exponents here, right? So if I integrate each of these, this is my result. Okay, here obviously I'm going to have to do the integration by parts. Okay, and this also needs to be done with integration by parts. I didn't show it here, but we've done this several times, so you know I use the Tableau method. If you like to use the formula, then go ahead and do that. Okay. The next thing I need to do once I've integrated everything, I need to do this, basically this result, and multiply it times phi, my fundamental matrix. Okay. So I'm basically going to take, wow, I don't need to go backwards because you guys will see it here. I'll take my phi times my result. Okay. And when I do that, I get this long thing, which makes sense again because I'm taking this times this and adding it together, right? So I'm getting basically 6 terms. These 3 terms plus these 3 terms, each respectively multiplied by this and this, right? So this is 6 terms. Then same thing here, when I take this row vector dot product with this column vector, I get another 6 terms. Okay, so I try to combine anything that I can, anything that's similar. So I have negative e to the t, negative e to the t stuff. I have t e to the t to the e stuff, e to the t stuff. Same on top. I have everything combined with at least something else. So that simplifies quite well to the following. Okay, so when I put everything together, remember this is my x of p. I get my generalized solution minus this particular solution vector. Okay, and that's my answer. So the homogeneous portion, the generalized homogeneous solution, and the particular vector solution. I put a minus here because everything here is minus, so I just factored it out. Okay, hope this was helpful. See you guys on the next one.